Avalanche likelihood is one of the key things that avalanche practitioners need to clearly communicate to each other. In this presentation, Scott Thumlert, Grant Statham, and I explore some ideas on how to communicate avalanche likelihood and probability more consistently. But these are just ideas in an evolving subject. We'll finish with some discussion points that need your input. To put avalanche likelihood in context, here is the framework for the conceptual model of avalanche hazard by Grant Statham and colleagues. This model is widely used in North America. After selecting the type of avalanche problem, for example, loose wet or deep slab, location is defined as where in the terrain the problem can typically be found. The forecast team then combines the sensitivity to triggers, which has 4 levels, and the spatial distribution, which has 3 levels, to get the avalanche likelihood, which has 5 levels. Let's look at 2 examples of spatial distribution. Assuming the specified location is alpine, this photo shows widespread avalanching, and this photo shows isolated avalanching. Clearly, the spatial distribution is part of avalanche likelihood.
Over the last 4 winter seasons guiding helicopter skiing in Canada, I had the opportunity to see how the conceptual model for avalanche hazard was working in the field. After a few discussions, call them arguments, with guides about the likelihood terms, we became interested in what other folks in the avalanche industry actually thought the likelihood words meant to them as percentages. So we asked avalanche practitioners from around the world, received 75 responses, for what they interpreted the likelihood words to mean about the chance of avalanches. What percentage comes to mind when you say likely? Here are the results. We see separate median values for each term, which is good. And these are also similar to what has been established in other industries. However, we see large ranges for each term and large overlap between terms. This could be problematic. How could one practitioner be thinking 10% for likely and one be thinking 85%? Here's some data from a broad survey about what percentages people associate with general likelihood terms. Our results generally match the broader population, with perhaps even more overlap between terms. There are likely many reasons for this, and the most obvious one is that the avalanche industry has yet to explicitly define probabilities for these words, which means avalanche workers have yet to be trained in what probabilities to actually use. It is worth noting that possible is not on this list, and overall the literature shows that it's a poor choice for a likelihood term because it does not actually indicate probability and thus creates a bit of confusion.
In the conceptual model, likelihood is defined as the chance of an avalanche releasing within a specific location and time period, regardless of avalanche size. However, Scott has shown that there is considerable overlap in the interpretation of probability for the 5 classes of likelihood. One reason for the varying interpretations may be that different operations and different forecasters interpret specific location differently. Some practitioners forecast for a few paths. Others forecast for regions with many thousands of paths. Probability estimates, and hence likelihood ratings by forecasters, are likely influenced by the size of the area that they commonly forecast for. Highway operations expect and observe fewer human-triggered avalanches than some backcountry and ski area operations. So, the number of backcountry users within a forecast area may affect the likelihood ratings. These are a few of the reasons that the likelihood ratings may vary for the same conditions.
Okay, there's good news for us in the avalanche industry. Many other industries and disciplines have been working on the problem of how to effectively communicate probability. Many disciplines, such as climate scientists trying to communicate climate change to the public, intelligence agencies creating standards across their whole agency, and meteorologists using probability in weather forecasts. The following few slides are the Coles notes from about 50 papers exploring communicating probability. So we can communicate probability with words or likelihood terms, something like no chance, unlikely, fair chance, sometimes, possible, 50-50, likely, and many other similar terms. The advantages of words are they are very good for fast communication between people. So for example, maybe Avalanche practitioners discussing Avalanche events in the field. So what are the disadvantages of using words? As their survey showed and the literature and research has established, likelihood words are interpreted differently by different people. They're also interpreted differently by the same people in different contexts. So maybe on a different day or when the people are in different moods. Likelihood words are also susceptible to self-serving interpretations. And finally, people prefer to communicate opinions verbally with words, but they also prefer to receive precise numerical information. Okay, we can also communicate probability with numbers. Let's say 0 to 1. 0 being that the avalanche is definitely not happening, and 1 being that the avalanche is definitely happening. Percentages are commonly used for this. The advantages of numbers are they can be more precise. For example, the probability of rolling a 6 on a dice is 0.16666, and you can write as many sixes as you want to be as precise as you'd like to be. Numbers, you can also accurately reflect your uncertainty by giving a range. So for example, the probability of that 5-week-old surface water layer down about a meter waking up tomorrow, let's say, is between about 5 and 60%. We're not very certain, and we can reflect that uncertainty with a range. What are the disadvantages of using numbers? First of all, they're slow. It takes time to understand, rationally interpret what the numbers mean, and then make a decision. Therefore, they're not that suitable for fast, intuitive decision-making of the kind that Avalanche practitioners may be doing in the field. Another disadvantage is that often the reference class is not specified. We'll explain what the reference class is using this example, 20% probability of precipitation in Vancouver tomorrow. How many people out there have actually wondered what meteorologists mean when the forecast states 20% chance of rain tomorrow? Do they mean it will be raining on 20% of the area of Vancouver tomorrow? Do they mean it will be raining on 20% of the time tomorrow in Vancouver? Do they mean that for each point in Vancouver, there will be a 20% chance of measurable precipitation? Or do they mean it will rain on 20% of days that are similar to the forecast tomorrow? Probably some folks out there know the right answer and some don't. Area, time, points, and days are the reference class in each of these examples. So we add confusion when trying to communicate probability when that reference class is not explicitly stated and defined. We can also communicate probabilities as frequency statements or rates. A frequency statement is how many out of how many. For example, data are roughly showing that on average, about 2 out of 100 people who get COVID-19 will be killed, or about 1 in 4,000 people who live in Canada have died from COVID. So people with COVID or people who live in Canada are the reference class for those rates. The advantages of frequency statements are that research has shown that people are better at interpreting and understanding these, especially for small probabilities. So what is easier for you to interpret? A probability of 0.00025 or the same probability written as a rate of 1 in 4,000? Also, for frequency statements, the reference class must be defined. So here is that same 20% chance of precipitation written as frequencies. Note the reference classes in each of these examples are defined. What are the disadvantages of frequency statements? Again, frequencies are slow, as with numbers, are slow and therefore may be difficult for fast, intuitive decision making. Also, they're perhaps difficult for single event probabilities. What is the frequency of that avalanche path releasing tomorrow? To summarize, there's a depth of research across many industries that has established that communication improves when likelihood words are explicitly defined as probabilities, the reference class is defined and stated, and the probabilities are in the intuitive range for what most people would associate with those words. Another important point for these probabilities and ranges is that they should be defined by the user group. So for the avalanche industry, we can and should define our own probability ranges that are useful for decision making in avalanche terrain. A good communication system for probabilities would allow the use of words or probabilities or frequency statements. The words would imply the probability ranges and the frequencies, and then these would be consistent across all people in the industry. To reiterate, these concepts have been shown to improve communication across many industries and disciplines.
Summarizing Scott's points, here are some things we should look for in an improved likelihood scale. The scale should be based on a relevant reference class that is independent of spatial scale. For each level of the scale, the likelihood terms should be associated with probabilities and frequency descriptions. The numerical probability ranges should be useful for making decisions regarding avalanche terrain. The terms and probabilities should be intuitive and consistent with well-established ranges. And here is an optional attribute for discussion. Should the frequency descriptions facilitate validation, that is, checking against the number of observed avalanches? Here is our draft definition of avalanche likelihood. Consider the avalanche paths or start zones in the forecast area, where the specified avalanche problem type is expected to exist. The likelihood of avalanches is the chance of those avalanche paths or start zones releasing within the forecast time period, regardless of avalanche size. For discussion, we float this scale that satisfies the attributes of an improved likelihood scale. To be useful for decisions regarding avalanche terrain, there are 4 levels. Likely is for when many slopes are expected to release avalanches. This term captures the uncertain middle range. This term is for when the problem is on the radar but unlikely. And this term is for low probability, avalanche problems we don't expect but cannot disregard. The scale is based on the reference class, which is the practitioner imagining the terrain within the forecast area, where the forecaster expects the problem type to exist. The practitioner then estimates how many of the 100 paths or start zones are expected to release avalanches of the specified problem type. The corresponding probabilities range from less than 1% to more than 30%. The frequency descriptions are not very useful for forecasting for a single path or an area with a few paths. In this situation, the forecaster should use the probability ranges or likelihood terms. This scale is simply a basis for discussion to give you a target to swing at. To get the discussion started, here are some points Grant, Scott, and I have been rattling around and not always agreeing on. Is imagining avalanches expected in N of 100 paths or start zones practical for practitioners to visualize or estimate? Or should the reference class be temporal? For example, avalanches in a typical path or start zone on N of 100 days. The scale goes from less than 1% to more than 30%, which covers 2 or 2+ orders of magnitude. Should the scale span more orders of magnitude? Last year's ski cutting survey showed the frequency of ski cutting varied over roughly 4.5 orders of magnitude. However, asking that a practitioner estimate the number of expected avalanches over 10,000 or more paths is likely beyond intuition. Should there be more levels at the high end of the scale? For example, should the scale have classes for likely, very likely, and almost certain? Or should there be more levels at the low end to better characterize the low probability, high consequence situation? Should the frequency of human triggering be excluded from the frequency descriptions, since it depends on the skill of the people traveling in avalanche terrain, compaction, and the number of people in avalanche terrain? Or should the practitioner estimate that people will be center punching the avalanche start zones in the 100 paths? If we assume center punching, then the frequency descriptions cannot be validated. In Schweitzer's validation study, he used Whichever natural avalanches and human-triggered avalanches were reported to the Forecast Center. Some countries are now counting avalanche deposits with satellite imagery, but that will not be affordable for many forecast areas in the near future. Since we don't agree on these points, we'd like your input to make this a better likelihood scale.